All right. Okay. Thank you everyone for attending. And I'm sorry, uh, I have a terrible internet connection at this point because I'm at home. But I'll try to say a few words about my recent work, which is joint with Nobuo Iida and Masaki Taniguchi, and it is about obstructing to embeddings in four manifolds using Bauer-Furuta type invariant. So one of the main results for this talk is following. So let me state the main result. So I'll not state the main result in full details, but a particular example I'll just state, which is as follows. So this is sorry, Ida, myself, and Masaki. So let's talk about a particular example. So let's say that K3. So let K be not in punctured K3. So let's say in S3, which is boundary of uh, punctured K3. So that means you take this four manifold, you take out a four ball out, and then you think of this knot sitting in the boundary. And if Thurston-Bannikin number of K is bigger than 0, then K is not H slice in K3. So let me explain these terms now. So notice that as a three manifold S3, it has a unique contact structure. So it has a unique given by Eliasberg. So in that sense, I can now talk about Thurston-Bannikin number of a knot in S3 loosely, in a sense that I think of this knot, the representation of this knot, a Legendre representation of this knot in this unique type contact structure, and then geometry. This Thurston-Bannikin number is nothing but the difference between Seifert framing and contact framing. You can compare these two framing. The contact structure gives a framing on the knot, and the Seifert surface of the knot also gives a framing of the knot. The comparison of these two knots usually denoted as Thurston-Bannikin number. So if the Thurston-Bannikin number is bigger than 0, then our claim is that it is not H slice. So before defining what is the meaning of H slice, and this is the main topic of discussion of today's talk, let me say a few words. So the first result of this kind in a smooth category was recently, so the first such result in smooth topology was first proven by Manolescu, Marengan, and Lisa Piccirillo. And we essentially generalize their result. So let me now say what is the meaning of H slice. So definition. So this is essentially defined by Manolescu, Marengan, Sarkar, Willis. So let K be a knot in X naught, and you think of X naught as again X. This is X minus B4. So you think of this knot in same as before, lying in the boundary S3, and we said K is H slice. So H is stand for homology. So if the following two condition holds, one is that K bounds disk delta in X naught, and secondly, if you consider the homology, this is actually trivial. The homology uh, of the disk is trivial in the relative homology group H2X boundary X with Z coefficient. Okay, so that is the reason this is called homological slice. That is, it is sort of homologically disappearing. Okay. Okay, so any question with the definition? All right. So in this talk, I mostly so in this talk, we will obstruct a sliceness in symplectic four manifold. Okay. So notice one more thing, that if X here, if X itself is a integer homology sphere, then H slice is same as slice. So H slice is then same as slice. And in that, for that reason, essentially people are these days interested in understanding the behavior of H sliceness, because that could potentially give a counter example of Poincare conjecture. Uh, okay, so let's talk a little bit now in the symplectic world. So one thing, notice that in symplectic for manifold context, there are some interesting known results about embedded surface in for manifold and their genus. Let me make it more precise what I'm trying to say. So if you know what I meant here, I try to indicate towards something called adjunction inequality. So let me state a interesting result in this context. So this is a result by Tom Broca and Rollin. So before explaining their result, let me state you the situation. So let's say we have a symplectic four manifold with boundary. So we have a symplectic four manifold X omega with boundary Y. Okay, so now under some nice condition, if the symplectic structure is nice enough, this omega induced a contact structure on the boundary. So psi. Okay. So now there are two things we usually see here. We usually first of all see the flow of the Liouville vector field. Okay. So the flow of the Liouville vector field in most of the nice cases either flowing normally outwards or normally inward. So if we are in the situation that this Liouville vector field is actually flowing normally outward, then this situation usually called convex symplectic four manifold. So the result of Moroka-Rollin is in this context, that if we have a symplectic four manifold X which is a convex with boundary Y psi, and now if K be a Legendrian knot in Y psi, and also we assume that since we are talking in general three manifold, we assume that K is null homologous. K is null homologous. And now let's say sigma be a Seifert surface for K, then we have this following relation, that all the characteristic of sigma plus Thurston Benneken number of K plus rotation number This is something absolute value of rotation number. This is always less than equal to 0. So what it is saying in particular, so now let's come back to the main interesting part. So what it is saying that if first and Benign number of k is bigger than 0 in this context, then that implies that k doesn't bound a disk. Or in the above definition, that's saying that k is not H slice. Okay. So this is a very interesting known result. Okay. So now, oh, all right. So anyone has any question in this definition or in this result? Okay. So now let's talk about the context we are in. So now what what we are interested in this case, right? So let's say now in our case we have a closed symplectic manifold X, and now we are taking out a 4-ball, right? Okay, so the first problem is following. Since we are taking out a 4-ball, now if we try to see the Liouville vector field flow line, it started pointing inward. Okay, so notice that here in the above result, the Liouville vector field actually flowing outward with respect to normal, but now we have this situation. Or if we redraw this picture as before, then I would say that this is the situation we have now. This is the manifold X, and the Liouville vector field is now flowing inward. So for this particular reason, there is no way we can generalize the result of so there is no obvious way we can generalize result of Mukherjee. So this is the first problem. Okay. Okay, fine. So there is not such obvious generalization, but one can also think in this way, right? But so for example, you can still imagine that, okay, fine, I can still cap this off with a 4-ball before, right? And now what is our objective? Our objective is following, right? So we have sort of a knot here. This is, let's say, our knot K, and we try to understand whether this knot bounds as H slice disk or not. Okay. So we can do following, right? We can kind of try to cap this off here with a cipher surface. And then now here we'll have now the closed 4-manifold setup. And for closed manifold setup, we have adjunction inequality. So then we can try to understand whether in this closed 4-manifold setup, this whole embedded surface, so let me highlight this. So if this whole embedded surface somehow contradict adjunction inequality or not. But now for that, there is another problem. So in the closed 4-manifold setup, in order to use adjunction, one important condition is that the surface we always consider has to be homologically non-trivial. But in our context, we are considering H sliceness. So the definition of H sliceness essentially says that this green element, the green disk, is actually trivial. And since I am capping off, here inside B4, this extra surface is also homologically trivial. So this whole embedded surface, it actually becomes homologically trivial. So this condition is also not satisfied. So as you can now see that all the known techniques so far we had previously actually failed to detect the H sliceness in this setup in a 4-manifold with boundary S3. Okay. So here now let me tell you a general result what we essentially proved. So this is the first result what we proved So maybe we can say that this is the first result, or so this is the first result or first Banach type inequality in the symplectic cap setup. So theorem. So this is the main result of our one of the main result of our paper, as Iida, myself, and Masaki, sorry, Taniguchi. So let X be a symplectic cap, or let's say X omega be a symplectic cap of S3 with standard contact structure, such that the first Betti number of X is 0 and thus B2 plus of X congruent to 3 mod 4. So if you know a little bit of four manifold topology, you know that the middle dimension of four manifold is most important one. In particular, we have a bilinear form over there, and under that we can see the space which are corresponding to +1 positive eigenvalues, and the rank of that is essentially denoted as B2 plus. So we need this extra condition that the B2 plus of this symplectic cap is congruent to 3 mod 4. And under this situation, now let K be a Legendrian knot with Banach bigger than 0, then K doesn't bound a disk delta with delta square bigger than equal to 0. So I would like to compare this particular result with the previous result, that is I stated here about Moroka-Rollins. So in Moroka-Rollins, we said that as long as Thurston-Banach number is bigger than 0, K doesn't bound a disk. Okay, but at the case of symplectic convex filling, where the vector field is kind of going out. But now notice that in our case, for a symplectic cap case, the only part I could say is that if K is a Legendrian knot with Thurston-Banach number bigger than 0, then the disk has cannot have self-intersection number positive. Okay, so definitely it is not as strong as the previous result for the symplectic filling, and maybe that is the reason why it took so long time for proving this result, because it's not true in various cases. So as I said that, so in this above result, you can see the two mysterious object, this object. So this condition is very important, as I will demonstrate that if I lose this condition, that is B2 plus congruent to X mod 3 is not applicable, then this following result actually falls. And also this other condition that I can only say one side, that is the self-intersection number positive, I can obstruct that part. In particular, I can also demonstrate that there exists knot which bounces disk and with Thurston-Banach number positive, such that the self-intersection number is precisely negative. Okay, so these two example I will demonstrate towards the very end, that and saying that this result is at its absolute strongest form. That is, if you change any of these conditions, the result falls. Anything else at this point? No, that is good. Okay, so anyone has any question at this point before I move forward? All right, so now let me say a little bit about how I should prove this, or what is our approach to proving this. So the main tool, and I'm not sure if my collaborators are in the audience or not. So, but one of the main tool is actually developed by one of my collaborator. So Iida recently introduced a four manifold with contact boundary invariant. So what does it saying that? So what he essentially introduces that, so let's say we have a four manifold W with Y boundary, and in particular I can fix a contact structure psi and a spin structure S such that they are compatible, in the sense that the induced spin structure by S on the boundary is same as the induced spin structure by psi on Y. In that situation, he introduced a map psi. We denote it as psi omega psi S. So this is a map he introduced, which mapping from some sphere with appropriate dimension to another sphere with appropriate dimension. And this particular map, in particular, he proved is as an invariant of the manifold W. Okay, so this is the result he proved. So again, I'm not here explicitly saying that what are these dimensions. Okay, so this is a little bit technical, and I don't want to go into extreme technical details of this invariant, but if anyone is interested, you can ask me later, or you can read our paper. We explicitly and very carefully wrote down all the details. But for the motivational purpose, I feel that I do not need to go into the explicit details of this invariant. Okay, so this is a nice invariant he defined. So now let's demonstrate some of the interesting property of this particular invariant. So let's say theorem A. So this is proven by Iida. Also, you can think of this theorem, this result as a non-vanishing result. So it is as follows, that if W be a symplectic filling of Y psi. So symplectic filling means symplectic manifold with convex boundary. So that is with convex boundary. That means the vector field is kind of Liouville vector field is going outside. So if this is the situation W, and also we need a small condition that V3 of W is 0, and let Xi be a symplectic four manifold with B 2 plus congruence to 3 mod 4, for then psi of W, psi of W connected sum x1, psi of W connected sum x1 connected sum x2, psi of W connected sum x1 connected sum x2 connected sum x3 are non-vanishing. So notice that all the known invariant, all the previously known invariant which are coming from various gauge theoretic point of view. For example, Sabo for manifold invariant or Seiberg-Witten for manifold invariant. All those invariant actually vanishes in this connected sum. For example, this example, Seiberg-Witten is 0, Sabo for manifold is 0, but this new invariant is actually non-vanishing. And it is actually non-vanishing up to 4 copies of connected sums. So this is the first result. So this is the non-vanishing result. And the new result we proved in this paper is following. Oh, before that, anyone has any question regarding this statement or regarding this invariant?
Actually, in this result, when you take more than 3 connected sums, what goes wrong?
Oh, yeah. So this is some kind of algebraic topological reason. So as I said that, so I kind of didn't go to the extreme details, but here I said that this invariant is a map between two spheres, right? So in particular, this map is nothing but a Hopf map. So this is nothing but Hopf map, and in the stable homotopy group of sphere. And this map is actually Hopf wedge Hopf. And this is Hopf wedge Hopf wedge Hopf. The problem is that the 4 Hopf wedge is actually trivial in stable homotopy groups. And for that reason, we cannot say anything about the 4 connected sum. I mean, 5 connected sum in this case. But I mean, we believe that that is also true, but just that this invariant cannot say anything further because the wedge product vanishes. Is that give your answer?
Yes, thank you.
Yeah, thank you. Okay, so that's one of the theorem. Now let's say theorem B. So now you can think of this as a non-vanishing result. Sorry, this theorem B you can think of as a vanishing result. So theorem B. So this is by Iida, myself, and Taniguchi. So you can think of this as a vanishing result. That if there exists a sphere S in W such that S is non-trivial in the relative homology with Z coefficient and self-intersection number is bigger than equal to 0, then psi of W is trivial. Okay, so okay, I cannot fit them in the same page. Okay, great, I can fit them in the same page. So now our goal is to play around with these two results. So as I said that, so theorem A is saying that this particular invariant is non-vanishing in various cases, and theorem B is saying that under this condition, that if there exists a sphere with self-intersection number positive and non-trivial, then this invariant vanishes. So using these two conditions, if we can come up with a contradiction, that might be helpful to then find out interesting results. So let me now demonstrate how one can come up with a contradiction and in a particular obstruct H slices. Okay, so our goal is, so let me say that here our goal is to obstruct H sliceness in symplectic cap. Okay. So what is the situation we have? So let's say this is a symplectic cap of S3. This is X omega, and there is a knot lying here on the boundary, and we try to understand whether this knot bounds a disk or not. Okay. So So okay, so now here is the trick I try to demonstrate here. So now let's say if I fill this S3 with a 4 ball B4. Okay, so now bear with me. I kind of didn't talk about the orientation yet, but now I have to be careful with the orientation. Okay, so first of all, notice that one thing, that when I'm thinking of this S3 as a boundary of this upper manifold, then that actually oriented in this way. Okay, so if I think of this not K in S3, then once I think of S3 as a boundary of B4, then that put a reverse orientation on S3. In particular, then from the bottom, when I see the knot, this becomes the mirror knot. So this becomes K bar. Okay. All right. So this is a small orientation issue. Please be careful while when try to deal with this, because we are kind of thinking of the boundary from two different perspectives. Okay, so now we want to obstruct this knot K from bounding this particular disk. So in particular, now if I take a small tubular neighborhood of the disk here together with this 4 ball, then this is nothing but the knot trace. So this green piece becomes the knot trace of K bar, right? So obstructing H sliceness in X omega is equivalent of if I obstruct embedding of X naught K bar inside the closed manifold X. Okay, so let me spell it out. Obstructing H sliceness of K in um, X naught is equivalent to obstructing embedding of X naught K bar in the closed 4 manifold X. Okay. All right. So now the question is, how do I do? How do I prove that this is not possible? So let's prove. All right. So okay. Before that, anyone has any question with this strategy? Okay. So proof. So what is one condition we assume? We assume that the Thurston-Banach number of the knot is precisely 0. Okay. So now this condition comes handy. Why so? Because Eliasberg and Gong proved that Eliasberg Gong proved that if Thurston-Banach number of knot is bigger than 0, then X naught K has a Stein structure. In particular, this is a 4 manifold with convex boundary. So you can think of 4 manifold with convex boundary. Okay, and our goal is what? Our goal is to obstruct embedding of X naught K bar inside B4. So let's say in this way. So let's say W is X naught K. So W is time, and W bar, if I reverse the orientation, this is nothing but then X naught K bar. Okay, and our goal is to obstruct W bar in embedding. Okay, so now the rest of the proof is essentially carefully drawing a few pictures. So please ask me question if anything is confusing. So I'll try to now draw a pair of pictures and try to now explicitly come up with an counter example. Okay, so let's start. So here is first of all, here is a small ambiguity. So let me say this clearly. So this is my W, and this is the boundary. But notice that so one thing I should go back in previous case, that here we need something on the relative homology. Okay, we need this. We need to come up with a sphere which is non-trivial in the relative homology. But in this case, if we consider x naught k, then the boundary is not a homology sphere. So there is no reason that I could, when I compute a relative homology, this is non-trivial. So just to make sure that when I do compute a relative homology, I still get something non-trivial, what I could do, I could attach a few more Stein handles on W such that this top boundary becomes integer homology sphere or rational homology sphere. So it's not a big deal to convert the top boundary to a rational homology sphere by attaching a few Einstein two handles. Okay, and that only contribute in the second homology group. So if we do so, the whole thing still stays Stein or convex. Okay. On the other hand, we have this closed symplectic four manifold X. Yeah. This is our closed symplectic four manifold X omega. And now we want to understand, we want to obstruct W bar in embedding here. So let's assume that W bar actually embedded here. And let's see if we can come up with a counter example. So let's say W bar already embedded here. Okay. Now what we can do, so now we can do this non-vanishing result, right? Because we know that, so let's say, so this is my W1, this is my X. So now I can connected sum. Since our invariant doesn't vanish under connected sum, so now I have the freedom to connected sum. So let's connected sum. Okay, so this is the picture I try to say, that please believe me whatever I'm saying, and also think about it, that when you do connected sum, you can actually do connected sum in following manner. So this is the picture in the two-dimensional setup, but the exact same picture hold for four-dimensional setup. So notice that I can take these two four ball out and then kind of draw a cylinder and connect them. If I do so, now notice that I have this piece. So my claim is that looking at this manifold, looking at everything under this is nothing but W boundary sum W bar. So what I'm trying to say is that the W boundary sum W bar actually smoothly embedded inside W1 connected sum X. Okay. So anyone has any question with this picture or with this claim? So this is proof by picture. So this is the claim, and the proof is the picture. This is the proof. So anyone has any question with this claim or the proof? Okay. So I have W boundary sum W bar embedded in W1 connected sum X. Okay. So now let's draw W boundary sum W bar in a different way. So what is the meaning of boundary sum? So by construction, W is actually X naught K, right? So W is nothing but you take a four ball and you attach a two handle along the knot K, right? With framing 0. And boundary sum means you just boundary sum another copy of B4, and W bar is nothing but then you attach a two handle here along K bar. Okay. And everything with framing 0. That's the best part. Okay. So now what I can do, I can slide one of these handle on top of the other handle. Okay, so this is the handle calculus I'm doing now. So if I slide this one handle on the other, I have this following picture. So this is again my boundary sum. This is my knot on K bar, but now my new handle, I slide over K. So this is my new handle. Okay, so now the question is, what is the attaching circle or attaching sphere of the new handle? So if I do so, notice that my new attaching sphere here have become now K connected sum K bar, right? because I'm sliding over k bar, so the new attaching handle become k connected some k bar. And the best thing about this particular attaching sphere is that this is slice. So this is slice means this sphere bounds a disk here, and with that I can now connect the core of the two handle, and thus I get a sphere, right? And this sphere is now embedded inside W connected some W bar, which is embedded inside W1 connected some X. And now with some homological argument, you can clearly see that this sphere is, by construction, is non-trivial in H2 of W1 connected some X with rational coefficient, right? So in particular, in the relative homology, this sphere is non-trivial. And also notice that the way I constructed this sphere, the self-intersection number is actually 0. So from here, so now theorem B implies then, so theorem B implies now that this invariant W1 connected some X is trivial. But the way we construct W1 and X, both are symplectic. So theorem A, so this is contradicting theorem A. So thus we get the contradiction of the fact that so our initial assumption was this fact, right? The W bar embedded in X. So thus we get the contradiction that W bar embedded in X, which implies that K doesn't bound H slice. Oh, sorry, K is not H slice. Ah, my bad. All right. Anyone has any question? Okay. So with the same argument, you can actually prove this result. So I'm sorry, what is the argument? Yeah. So with the same argument, you can actually prove this result explicitly. So I'm not proving this, but now I'll demonstrate why these conditions are important now. Okay. So now I'll demonstrate that why these two conditions are important. So let's talk about the first here, that why these conditions is important. So let's talk about that. So notice that so consider right-handed trefoil in K3 boundary. Okay. So if you know a little bit about contact geometry, then it is not difficult to compute the TB number, and in particular the TB number of right-handed trefoil is 1. So by our result, we can say that the right-handed trefoil is not H slice in K3 bar. But here is an interesting result proven by Manalescu, Moringham, and Piccirillo. And I improved this result a little bit. So the result is as follows, that if K is not in K3 bar such that the unknotting number of K is less than equal to 2, then in particular I improve this result by unknotting number less than equal to 4. So unknotting number means you do 2 crossing changes and that gives you an unknot. Okay. So unknotting number is less than equal to 4 in particular, then k is slice in punctured K3. So now if you know right hand trefoil, then you know that the unknotting number of right hand trefoil is 1 in particular. So unknotting number of right hand trefoil is 1. So that implies that right hand trefoil is slice, and that means it bounds a disk. So this is one interesting example of a smooth knot which is not H slice but slice in K3 bar. Okay. And for that reason, you can see that why this condition is important, because this, since it's slice, that means it also bounds a disk. The only thing is that the self-intersection number of the disk is now negative. Okay. And now the second condition is that this B2 plus. So again, notice that if you know a little bit symplectic geometry, then you know that E1 is a famous elliptic surface, which is CP2 connected some 9 CP2 bar. And then this claim is that every knot, it's my bad. The claim is this, that every knot trace can actually be embedded in E1, and that's saying that every knot can bounce then a disk with self-intersection number 0. So every knot can bounce with self-intersection number 0. Okay. All right. Any question? I think I still have 5 minutes, right? If I'm not wrong.
Yeah, you have like nine minutes.
Oh, okay, great. All right. So now, so this is the first part. So now one small part I would like to mention is about exotic 4 manifolds. So now let's talk about exotic 4 manifolds. So this new invariant also can detect exotic structures on 4 manifold. So here is an interesting question I would like to propose. So question that, does every 3 manifold bound a 4 manifold which has exotic structures? So in recent time, people have been shown tons of interest in understanding exotic structures in with 4 manifold with boundary. And this is a very obvious question in that direction, that whether given any 3 manifold, how do you construct a 4 manifold which is exotic structures? So a little bit history. So Yasui, using Seiberg-Witten theory, proved that Stein-Fillable 3 manifold, in particular symplectic, sorry, let me say stronger phrase, proved that symplectic, sorry, that all 3 manifold which has a strong symplectic filling bounds exotic 4 manifolds. Although he didn't publish, if I'm not wrong, this work, and independently. So independently, Jonathan, mean, Hyunki mean, and myself, we prove a little bit stronger than this result. So let's say the similar result, but a little stronger using Higger floor theory. And recently, we came up with a much simpler proof using this new four manifold invariant. So that is what I try to say now. So theorem. So I'll just state the most easiest form of the result, that is if Y admits a Steinfillable um, contact structure, then Y and Y bar bounds a four manifold W with exotic structure. Okay, and in particular, the examples we demonstrate here cannot be detected using Seiberg-Witten and Higger floor theory. So how do you prove that? So as I say that by assumption, we know that Y has a Stein filling. So let's say this is your Stein filling of Y. And then you just connected some with K3, connected some CP2 bar, just connected some these two copy. So this is your W, and you take the same simplex Stein filling, but now other than connected some with K3, connected some CP2 bar, you connected some with 3 CP2, connected some 19 CP2 bar. So notice that, so this is, let's say, W prime. So notice that W and W prime are homeomorphic. So this is easy to prove that these are two homeomorphic. So the main difficulty is proving that they are not diffeomorphic, right? But now notice that the new invariant psi here is non-trivial, right? Because one piece is Steinfillable and another piece is symplectic, so psi is non-trivial. But in this piece, in 3 CP2 connected some 19 CP2 bar, you can easily construct a sphere with self-intersection number 0 and non-trivial sphere in particular. And that's saying then that psi is trivial. So this implies it is exotic. So they are not diffeomorphic. Okay. Okay. I think this is the best time for me to stop, and I'm happy to now answer questions anyone has.
So actually, I have a bunch of questions, but first, let's the speaker again. Talk. Thank you very much. Are there any questions?